All right, excuse me. Can I have your attention? Yes, it's time to start. Yay. All right, so let's take a look at where we are. We have our course thing here. Now today, the lab today is going to be to turn in the first 100 lines of your final project. Now this can be pretty simple, right? You can make a tweak on your lunar lander. You can make a tweak on my flyer or something like that. You don't really have to do much. But there is this little verification website which you can go to and test to see if you're doing things the way you should. And what it's going to want you to do is it's going to want you to upload your code as part of the basic graphics package. So I want to see all my code again, because what frequently happens when students make these projects is they wind up modifying my code in mysterious ways, and then it just becomes difficult. So this is going to check your images. It's going to check your code. It's going to check a bunch of, it's going to do your, it's going to do a base level line count for you. The TA is free to modify that line count if he sees lots of repetitive code. In any event, that's sort of to try and get us on the same page, get something that works approximately correctly. So pay attention to that. And if so I hope to see you there tonight in lab, and we can help you work on your basic graphics. Or if you have any other course problem, you can treat it like an office hour, and I'll be there, and you can harass me in whatever way seems appropriate. All right. So let's take a look at the schedule. Today is Valentine's Day. Happy Valentine's Day. All right. And coming next, we have more recursion. We have time complexity, searching and sorting. Less talking, please. Less talking, please. We have more time complexity. We have more time complexity. We have a review, and we have a midterm on the final class of the month. I have to time the midterm in times to get your midterm grades in. I know your other professors don't bother to turn in midterm grades, but I'm going to do that. I'm going to turn in a midterm grade. It's going to be based on your quizzes and tests to the point in the course. It should give you a good indication of where you're going to wind up at the end of the course. So, be prepared, be ready, do well. Okay. Let's go to the recursion. And where were we last time? Oh, I went in and filled in the links on these codes. I thought I'd done that before, but I hadn't. So I guess this is where we were. Yes. Okay. Slideshow. Okay. So a lot of these slides in this course are, here are the codes. Let's look at the codes, right? And let's walk through the codes in detail. So last time we did Towers of Hanoi, and we talked about group sum 0. What we want to do today is kind of more of the same. So so we looked at Hanoi, right? And the essence of the Hanoi code was in this move n method, right? Where if we want to move n things, we do it by moving n-1 things. And that's sort of your metaphor for how all recursive problems work, right? You do n things in terms of n-1 things. If you add to that the ability to do things when n equals 1, then you're done. All right. So in this case, the program we looked at the end of last class was to find group, was called find group. And what it's going to do is going to find whether an array full of values contains can be used to make a sum, a given sum. So it's kind of like a change making problem. And we walked through how it worked. Basically, what it does is it tries 2 times with each value. First including it, then not including it. And including it means that we subtract val from the sum. So like if the current coin, as it were, is 5, and we're looking to make 50, and we're gonna say, okay, if I'm gonna use this one, then I only need to make 45, and then I work from there. Okay. So that's the logic of that. Now let's see it in action. So we have our assertions that should be true, and then we have for n equals 0 to 25, we try to make the number. So let's do that. I don't think we had a chance to run it. Ta-da! All right. So what you see, true, false, false, true, false, true, false, true, true, false, true, true, true. So there's lots of trues, right? Like 15. Let's just think about 15. Let's go back and look at that. So how do we make 15 out of this? Well, 5 and 7 and 3, right? And without recursion, I think it would be pretty challenging to make a piece of code that could figure this out. You should be able to do it. It just would be a lot more complicated. All right. In principle, you should be able to do any recursive code without recursion. But in some cases, it's just very difficult to imagine how to do it. All right. Let's take a look at the next one on our list. So we have group sum 1. Now, the nice thing about this basic group sum problem is I can make like a million variations on this, right? And you can imagine, and it could even be that you have to code something similar to this in your real life someday. Maybe it's a game where you have to your characters have to make change. Maybe it's something different. All right. So let's see what goes on with this one. So what's going to happen here is I have a different task set for myself. The idea is I want to find out if some combination of integers in nums adds up to the target value. But if I use an integer at position I, then I'm not allowed to use the integer at I plus 1. Right? I'm not allowed to use the next one. So if I have a list of 2, 1, 5, say, as you can see on the bottom of the screen, if I use 2, then I can't use 1. If I use 1, then I can't use 5. Okay, those are the rules that I added for myself. And it turns out that I can implement this by changing one line of code and adding changing one character on one line of code. Okay, and that one character is this number right here changes from a 1 to a 2. Right, that's my position in the array. So group sum, right, with a value subtracted means that I'm using that value. So if I'm using that value, then the next value I should consider is at the +2 position. Does that make sense? Right. So the idea is you have to look at these things and you have to think about how they work. All right. Yeah, and then also let me point out again, I have my exit conditions, right? If I've reached the target value, then my target is going to be 0, right? Because each time I take something off, it gets closer, hopefully, to the sum I'm looking for. And if I actually reach it, then that's going to be 0. And the other way that I can fail is if my start becomes greater than or equal to nums.length. So if I'm being told that my position that I'm going to look for something at is past the end of the array, then, and I haven't reached my target sum, which I haven't because I didn't exit on the previous line, then I'm going to return a false because I have failed. And no recursion is going to work if I don't have a bailout condition like that. Okay, questions? So I know there are people who sometimes tell me that they're lost. And what those people are doing right now is they're sitting quietly being lost. And this is not how you succeed. You know, one of the things I was reading an article the other day about people with messy homes, and mine is not perfect, but they say that a lot of times what happens with people with messy homes is that they look at the state of their dwelling and they feel so overwhelmed they give up just by looking at it. And what can happen is I think you can look at the course material here and you say, I'm so far behind, I don't know anything that's going on, you know, I'm overwhelmed, I'm not going to do anything, I'm not going to study, I'm not going to try to write code, I'm just going to sit here and you know, breathe heavy. So the thing to do when you're feeling overwhelmed by a task is to do just one thing, right? To pick out one thing to do. So if it's your house, you pick up, you know, a few dishes. If it's the code, you say, well, there's one topic Professor Brandt gave us. I'm going to understand that one topic. I'm going to ask one question in class, right? If you can do that one thing, it will help to start to reorganize your brain to get it to a better place. So, any questions?
Can you please go over the Boolean res equals group sum start +2?
Yes.
Can you
Okay.
go over
So
that block again?
yeah. So the question is to explain the Boolean res. And what's going on there is first I'm calling group sum with the idea that I'm going to use the value, right? And if I use the value, then I need to know whether that succeeded or not with looking at the rest of the values. So what's going to happen is it's going to go through the rest of that array and it's going to try including and not including every single value that follows. And if it succeeded, then I know that I'm done, right? So I shouldn't do anything else if that succeeded because I am done. On the other hand, if res is false, then I know that there's no way that using the current value that I can get to the sum that I'm trying to get to. So I have to try not using it, right? Because maybe it's too big, right? Maybe you know, maybe I'm trying to make 5 and this particular value is worth 15. No combination is gonna get me there. So I'm going to try again without using it. And so that's the meaning of res. And either way, right, if I succeed in either test, then res is going to be true. And that means that the group sum should return true because it is possible to make that sum with that set of integers. Does that help?
Yes, I think I got it now.
Okay, good. All right. Don't let yourself not get things that I say. That's why we have a classroom. Yes.
Could you re-explain the?
I'm sorry, name?
Bo. Could you re-explain the start +2 again?
Yeah, the start +2, the point is, right, I want to not, if I use a value, the assignment here is if I use a value, then I can't use the next one, right? So if I'm using the value, instead of advancing the position by 1, I advance it by 2, and that guarantees that I won't use the next one. Make sense?
What's your check for, like, if there's no possible values, then it just won't work?
Well, the check is going to be at the top, right? If I get to if I never hit this line with target equal to 0, then it doesn't work, right? Because each time for each one I'm trying subtracting it, and if I ever get to 0, then I'm done. So if this particular thing has 5 integers in 5 integers in the array, this will explore 2 to the 5 possibilities, or 32, right? And because it's going to try on and off for each one. If it has 100, it's going to try 2 to the 100, and then it probably will take a long time to figure out. But it doesn't scale to that. Yes, Scott.
For the res, it's looking at 2 if res is true, and if res is false, if it doesn't add up, then the next time it's only going to move 1 over. Is that correct?
Right, because I don't have to skip the next one if I didn't use the value. Okay. Oh, we should run that one. All right, so 215, I could make 7, and 589, obviously I can't, right? I can probably come up with better tests than that, but those are the tests I came up with. And okay. Okay, so it's great that I know that there is some set of integers that can do this, but what if I want to know what they are? It doesn't tell me what they are. How would I do that? Anybody have any thoughts? You save the values that you use to a new array. And what if you, when is it safe to put the values in the array? When is it safe to do that? I mean, so that you know that you don't, like you're going to try using it and try not using it. When are you going to put a value into the array? Okay, well, any other thoughts? Yeah. No? Anybody have a thought? How you would do this? Yes. Well, I currently don't return the values, right? The question is, how can I return the values? What do I need to do? Do you have an idea? Okay. What's your name, please? Christian. Okay, so printing it is one way I can do things, but put yes, Scott.
Make a static integer, and each time you do it, you add it to that static integer. At the end, you'd have a static integer with the sum.
Well, I'm not looking for the sum. I know the sum. I want to know the values. I want a list of the values. All right, so let's just think about this a little bit. There is a point in the code when I know whether I'm going to use a value, right? When that first group res, when I call it use the value, if that returns true, that means I'm definitely using that value. So I can add it at that point. So, all right. So there's a little more to it than that. So the way we're going to do this, okay, we're going to have find sum is the name of our method. We're going to have our array of data and our target sum. And this time, what I'm going to do is I'm going to create an array list. Now I'm using, on the left-hand side here, I'm using list because list is an interface and it's more generic than array list. I could put array list here. It really doesn't matter that much, but it's sort of good practice to use the interface on the left-hand side because that way, if I want to change the type of list later, I only have to change one line of code. So what I'm going to do then is I'm going to create a new kind of sum for myself. And that sum is going to take the data. It's going to take the target sum. It's going to take a starting position, and it's going to take this array list. Okay. Lesson. All right. So now what I'm going to do is when I call this new one, I've now got these 4 arguments. So my helper method this time is going to add 2 arguments instead of 1. And inside my helper argument, I'm going to say, I'm combining my 2 tests that I did in the other things into one. So what it's going to say is if the position is greater than or equal to the data.length, return target sum equal 0. So if I've gotten to the end, then I evaluate the target sum and I return it. So that's a way to combine those tests. Potentially this is less efficient because I could bail out sooner with the other method. Here I can't bail out till I get to the end of the array. By doing it in 2 steps, I could bail out in sooner than the end of the array, but either way will actually work. Okay, so then I call find sum. And what I'm going to do is I'm going to capture the return. I called it res in the last code. I call it B here. So I'm going to do the same thing that I do before. I'm going to subtract the current value that I'm looking at from the target sum and advance the position to +1 and pass the list without doing anything to it. But if B is true, then I'm going to do a list.add of the data position, and then I'm going to return true. And otherwise, I'm going to just call this again without using the value. And I know that since I'm not using the value, I shouldn't consider adding it to the list. So that's how I do it. Look how simple it is. Questions? Don't let yourself be lost. I know there are people in this room who are lost, and I have some idea who some of them might be, but don't let yourself be lost. All right. So I made a test method for myself. Okay, and in the test method, oh, one thing I could do, one thing I could do with this that I don't do is I don't return the value of find sum. I compute this true and false value, but I don't return it. I don't do anything with it. And it's kind of hard to do because Java only lets you return one thing, right? And I'm returning a list. And you could say that if I return an empty list, then there's no way that I can build the thing. And you could just use that. On the other hand, if I wanted to, if find sum returns false, I could return a null, right? So that's another thing I could do. If I wanted to, or I could just accept, I could say list equals empty is gonna mean I didn't find it if the sum I was looking for was something that was not 0. All right. So I made a test method for myself because you should always test your code. If you don't test your code, it doesn't work. And I'm going to take the data, the target sum, and whether or not it should return a found, right? Whether it should succeed. And so I'm going to get the list I'm going to call find sum and get the list. I'm going to put a sum equal to 0 there. Then I'm going to say for integer a and list sum plus equal a. And I'm going to say if found, assert that sum equals target sum. And then I'm going to print it out, and else I'm going to assert that the list size was 0. So the idea is, right, that I'm not trusting it this time, that it succeeded in finding a list of integers that actually add up to the target sum. With this version of the code, I am checking. I'm getting that list. I'm adding up the numbers and verifying that it does indeed match the target sum. And now I construct some tests for myself, and the tests look like this. So I have 3, 5, 7, 9. Can I make 16 with that? Yes. So I put it true there. 3, 5, 7, 9. Can I make -1? No. 3, 5, 7, 9, 13, and 21. Can I do that? Well, I say true. Let's see. How do I do that? 13 plus 7 should do it. Okay. Let's see what it does. Ta-da! 9 and 7 is 16, and 13 and 5 and 3 is 21. That wasn't what I came up with. In fact, I think what I said was wrong. So this is why we have computers. Any questions? I can't believe nobody has a question. So enhanced for loop, the enhanced for loop in the test method, right? Any of the built-in collection types are able to be used with an enhanced for loop. And you can declare a variable of the same type as an element in that collection, in this case, a list. And then it will figure out the code that goes here. As we know from our previous class, the way this works is how. Who can tell me how this enhanced for loop works? What code does it expand to? Yes. Your Vanik?
Yes.
Okay. Yes, it's the iterator, right? You remember that? So this code, that this enhanced for loop that's sitting right here, what happens, the way this is made is we get iterator integer iter equals li dot iterator while iter dot has next sum plus equal iter dot next, right? This is what that code turns into. This is how Java understands that code and how it remaps it. Does that make sense to everybody? And this will also, of course, work with any iterators you decide to build. Any list iterator iterables that you decide to build. Okay. Any other questions? Yes, Manny.
You go to the top portion again.
Yeah. So the basic idea is when I call find sum and I subtract the target value that I'm looking at, right? In this case, data at position pos. If I return a true from that, that means that the thing has already gone through the rest of the list. And it has found that, yes, indeed, this particular path through the integers gave me the sum that I was looking for. And so it is safe to add that on at this point because I know I've used it. And if I didn't, and if that doesn't return true, then it definitely isn't in my list of things. Make sense?
Yeah.
All right. Anybody else? All right. Okay, let's take a look at my next code. This is a very complex code. Hello world. Can we do it? Can we do hello world? It's just a little different than the normal hello world. Okay, and in this one, I'm going to actually say hello in a bunch of different languages. I've got hello, I've got ciao, and I've got ni hao. Three different ways that we're going to call this. So the first one is hello iter. And hello iter is at the top, right? And what I'm going to do is it gets an integer n, and I just go through a loop for I equals 0, I less than n, I plus plus, and I print out hello plus I, right? Hello plus the number. If when I look at hello without anything special, right, then that's going to call this method. And what does this do? This calls another hello. It's got a helper method, right? And the helper method adds an integer position, just like we did in group sum. And what this one is going to do is it's going to go down to this call here next. And it's going to say if I is less than, so this is a, all right, I'm running out of power, but I have a call. This time I don't have to end the class early because I ran out of power. All right. So what's going to happen is I'm calling with the helper method. Now, whenever I do a recursive method, I have to be able to bail out. So in this case, I'm going to be careful to say if I is less than n, I'm going to continue to execute. Otherwise, I'm not. And so in this case, I'm going to say ciao plus I, and then I'm going to call hello plus 1 and n. Now, hello 2 looks kind of similar, right? If I start at the top here, in fact, it kind of looks exactly the same. I've just stuck a 2 on the end. But this method is different than this method, right? And what's different about it? Lucian, yeah, the things are flipped, right? The order that I made the calls to hello are flipped. Right. And so what difference does that make? So let's look at this. So the thing that we want to, the first one, which is English, we think we understand, but this Italian and Chinese ones, we may not, right? So let's see what they do. So the English and the Italian are counting forward, and the Chinese is counting backward. Because they read the other way. Yes, that's the explanation. No, the explanation is so the explanation is the ordering of these calls, right? So again, if you think through how the code is behaving, this should make sense to you, right? So what's happening is in the hello method, or with the chow, right? I come in here with I equals 0. I is less than 5. So I'm printing chow 0. And then I'm calling hello with a 1, right? And then when the 1 comes in, I is 1. I is still less than n. I'm printing the chow of 1. So 0 and 1, you can see, you just follow that through. It happens one after the other. Now, on the other hand, with hello 2, I come in here with 0 and 5, right? 0 is less than 5, and now I immediately go to hello 1. Okay, so I go to hello 1, and hello 1 is less than n, and I go to hello 2, and hello 2 is less than n. So I call the next one hello 3. Hello 3 is next than n. Next is less than n. I call 4. Hello 4 is less than n. I call hello 5. Hello 5 is not less than n. It returns without doing anything. Hello 4, now hello with a 4 argument can now proceed to the next line and print ni hao 4. And then it returns. And now hello 3 can proceed to the next argument and it prints ni hao 3, and so on. So the ordering of the recursive call matters, right? It's because of the stack, right? So what happens with a recursive call is we have something called the stack. Who knows what the stack is? There's one person, presumably, yeah, I was going to say presumably you did, because you were the one who said it. So there are 2 people in the room who know what the stack is. That's it. Okay. So the way a computer works, the way a function call works, right, is we have some temporary variables here that only are in scope for the call of the method, right? And what we do is we have a special kind of memory called the stack. And the way the stack works is whenever you allocate memory, you increase this stack, right? Whenever you deallocate memory, you decrease the stack. The idea is you always deallocate in the opposite order that you allocate. And that's because when I call a method, I allocate its arguments and something called its program counter and some other state, right? And when I return from it, I drop back. So I call, I return, I call, I return, and so on. Make sense? Now, I'm not sure anybody online can see me moving my hands like that, but that's the idea. The stack gets bigger every time I call something, and it gives things back every time it returns. And the program counter is a thing that tells it where it is in the instructions of your code, which instruction is going to execute next. And so every time you make a function call in Java, you grow that stack. And in the ni hao program, when I call that thing, the stack goes all the way up to the top of 4 things on that same method is on the stack 4 times before it starts to print out. And then each time it prints out, it drops a piece of the stack. It frees up a piece of the stack. Does that make sense? All right. So that's the mental model that you can have, because that's what the machine is actually doing. And if you build if you make a recursive method that doesn't have one of these bailouts in it, then you will get a stack overflow error, right? And that's an error that you probably should not catch, because if you run out of stack space, there's probably nothing that you can safely execute anymore. Your program is just dead. deal with it, pick up the pieces, move on with your life. Maybe we should do that just so we can see it happen. Let's say true. There we go. Now our Chinese speaker is going to infinity. Boom. And if I try to scroll up, I can just keep scrolling up. And it just says that same thing, because it's with what happens when my program fails is it prints out a stack trace, right? It's showing me each function call and line, and it's just calling the same thing over and over. And this is what an infinite stack looks like, right? When you just
catch statement to do that, or?
no, this is the default behavior. There's no catch, and we haven't talked about catch. We will, but we haven't. All right. It's fun to watch things blow up. Does it blend? All right. Any questions on any of that? Yes, Cooper. A stack is just a chunk of memory that gets allocated when a function is called, right? And that memory, because it's always freed up in the reverse order of how it's allocated, right? It can be implemented as just a simple linear position in a big block of memory. So if I want to allocate to the stack, I need two integers in this case. 2 integers is how many bytes? It's 8 bytes. Each integer is 4 bytes, right? So it's 8 bytes. So I add 8 bytes plus another, say 8 bytes for the program counter. So I increment that by 12, right? And then I return the pointer to that memory. And that's how it works internally. Right? Make sense? A little bit? Okay. A little bit. But it's a chunk of memory that gets allocated every time a function is called. It's the basic statement. And that chunk of memory, it has a line associated with it and a file associated with it. And when Java dies, right, it gives you back that information. It gives you the stack trace and prints it on the screen so that you can see where so that you have a chance of figuring out where your program died and why it died. All right. In this case, when I see the same thing over and over, I know what I did. I made an infinite recursion error, or something that was so close to infinite that my machine just couldn't handle it. All right. Anything else? Anybody else have a question? All right. So who knew that hello was as complicated as that? You'll probably have a quiz question modeled on that bit of knowledge somehow. For those of you who are paying attention, that will help you. All right. Permute int and triangle. Let me skip permute int for the moment. I'll come back to it later. Triangle is fun. Let's see if it runs from my window here. I think I set it up so it will. Look at that. Isn't that pretty?
It looks like an optical.
Yeah, well, so what I've done, in case it's not obvious, and the code unfortunately is a little obscure for this, but we'll take a look at it. But what I've done, right, is first I draw a triangle, and that's sort of my starting point. And then what I have to do is on each face of the triangle I've just drawn, I'm going to draw a subtriangle. So far, I haven't gotten anything that can recurse. But now what I have to do is I have 3 things, right? I have this basic direction that I'm facing. And I know that I'm going to draw 2 subtriangles that are each half the size of my current triangle. And so I have a method that takes this position in this direction and this size, right? And then it can divide that size by 2 and recursively call that same method here, and then here, and then here, and then there, and then so on down to smaller and smaller triangles. So you can make this weird, funky image with recursion. And unfortunately, you know, it's got a lot of trigonometry that you have to work through to make that happen. And I don't think we need to do that line by line, but you can sort of see how this is going to happen, right? So you remember the polygons from your lab. I'm going to draw the 3 points from my triangle. Then I'm going to draw the 3 subtriangles. And then I'm going to call paint triangle. And I'm going to pass my graphics object, an X and a Y, an angle, a size, an iteration number, right? Because I don't want this to go for infinity. So I have an N that I'm keeping track of. And I forget what that last true false argument. The true false argument is whether I'm drawing a red or a blue, right? Because I have to alternate. I could put an integer there and alternate between 3 things if I wanted to. I could change it up that way. But those are the things I have to pass to my recursive function. And yeah, so I call that twice. And the paint triangle method, or call it 3 times actually. And if n is 0, what's that?
Where's the stop?
If n equals 0, return. Right? Each time I call that n with a -1. So that's the stop. All right. I just, that one's just sort of a fun one since you've been looking at, you know, adding integers up. You know, that's great if you want to be an accountant.
Pause for 2 extra nanoseconds. You could see it build.
Yeah, that's right. If I put a pause in there, I could see it build. No one asks you questions if you say that you're an accountant. Okay. All right. I don't want to dig into permute right now because it's a little involved. And let's take a look at fib2 and fib3. So fib.java, I think we've seen this before. It's a very simple function, right? If n is less than 2, we return. Otherwise, we add n-1 and n-2, right? Now that's fine, except it's very inefficient. So if we want to be more efficient, we can do this in an iterative way. So very often, if you've got a program that's written in a way that is recursive, you can also figure out how to write it in an iterative way. And in this case, what I've got, right, is I've got if n is less than 2, return, and I've got fib m-2 and m-1 as a variable. And what I've done is I've created a loop, right, that goes from 2 to less than n. And I say that fib is equal to fib m-1 plus m-2. And then I copy fib m-1 to m-2 and fib to m-1, and I can keep that loop going. So in this way, I can do my Fibonacci, and it will be more efficient. And the difference is, right, if I run Fibonacci this way, you see that it gets up to 42, 43. It's already working very hard. 44, it's barely making it now. And every time it advances to another one, it has to do twice as much work to continue. All right. And so I'm never going to figure out fib 100 on this computer doing it this way. I'm just not going to happen. So let me kill that. And now we run Java fib 2, and it's done up to 100.
Pause, or was that just you're being slow trying to figure it out?
The first time it was actually slow trying to figure it out. It had so much work to do that it took that long, right? Because it had to, every time I added 1, I had twice as much work, and that adds up quickly. In this case, though, with the iterative method, it's linear. and the amount of work to do the next number was almost nothing. So you have to do a balancing act when you write recursive routines. You have to be aware that there's a potential efficiency payment that you're making. And if you're doing a Fibonacci number, well, you're calculating Fibonacci numbers and you're doing that first way, there's something wrong with you. Let me take that back. There are many things wrong with you. No. So no, if you do it that first way, you don't care about efficiency, right? Sometimes clarity of code is more important than efficiency. And I think that first one is exceptionally clear. And it doesn't take much work to get there. The second method is something that you are concerned with if you've got an application, say, that relies on this Fibonacci number and it's slowing you down to wait for it to compute. So you might not even try the second method until you'd already had some trouble with the first one, right? Because the first one was clear. And most of the time, if I'm doing Fibonacci of 15 or less, yes, it's inefficient, but who cares? I mean, the computer can do things quickly. It's not, there are people who worry about the amount of energy that you're consuming given greenhouse gases, but really, well, I believe that, I'm not a climate denier. I believe in greenhouse gases are a thing, but I think micromanaging how many calculations you're doing on your computer is not going to have any impact, right? This is kind of like having your Diet Coke worrying about that is like having a Diet Coke with your cheese stuffed crust, extra meat, Pizza Hut pizza when you're on a diet, right? The Diet Coke really isn't going to do anything for you at that point. So that's my thought on computation and global warming. I think for whatever it's worth, my opinion is we will solve global warming through technology. I'm not sure how that's going to look, but I think we're going to figure it out. All right. That's it for today.